Okay, so number 5. 10 different families are tested for the number of gallons of water a day they use before and after viewing a conservation video. Construct a 90% confidence interval for the mean of the differences. Okay. It's an interesting little question. They're matched up, aren't they? Yeah. Why is it that like these two and then the next two, etc., are matched? What is it about them that matches them? This one is a matched pair, but let me give you a caution. You can't just say, well, there's a table and there's the same number, so it's matched. No, I'll probably give you on the exam, at least it's on some of my versions and on the final, ones that have the same numbers that are not matched. It's got to be from the words. Remember, we're about real understanding, not monkey see, monkey do, but really understanding. So what in the words tell us that the data is connected, that they're matched up? Yeah, this is 10 different families. So you can't get away from really understanding the paragraph of the problem. So you want to keep, don't try to avoid that and just jump into the other stuff. There's important meaning in those words. 10 different families. In other words, this is one family. Before watching the video, they used 33 gallons of water per day. After they watched the video, they cranked it up even higher. They weren't very convicted by the video. The next family, they used 33 gallons of water per day before watching the conservation video. And afterwards, looks like they decided to save more water, and they went down in their water usage. Anyway, my point is those are matched up, right? It isn't like they just took 10 random families, and then 10, before and 10 after, 10 totally different families. They could have. You could do a study that way. But this is a matching up. This is the same family before and after. Before and after problems are always matched pair. I even put it on the list, didn't I? Somewhere. Oh, right there. Yeah. Before and after. Right there. If it says before and after, that's almost always matched pairs. Yeah. All right. So what do we do for that then? Data in L1 and L2, and then we're going to do the special thing where we do L1 minus L2 stored in L3. Remember that? And then t-test. So let's do it. So put this data in L1 and that data in L2. And so put the data in L1 and L2, and then we go, and then you got to quit. So after you put that data in L1 and L2, you got to hit second quit to kind of get out of the table mode, It's right above the mode key. And then you've got to do L1 minus L2 stored. You got to do the store button, which is over on the left edge above the on, into L3, and hit enter. You got to take the differences, right? Is what that'll do. And so what that'll do is that'll form all the differences and pop them into L3. And then, yes, you do t-interval. So what it says over here on the exam 4 notes. It's either t-test or t-interval. In this case, we're doing an interval, confidence interval. So we do t-interval, choose data, and 0 for your mu 0, 0, and your list is L3. Well, we won't even have a mu 0. So t-interval. Choose data, because we have a bunch of data. And make sure your list is L3, right? Because that's where the data set is now. And your confidence level looks like it's 90%. Calculate. I'm getting 1.7595, comma 7.8405. So it's this one right here. And there we go. All right, so on to number 6 we go. The table below shows the weights of 7 subjects before and after following a particular diet for 2 months. Before and after, same thing again, huh? This is going to be matched pairs because those are the same people before and after their diet for 2 months. But this one's a hypothesis test, not a confidence interval. So same thing, put the data in L1, put the data in L2. Yeah, so put L1 and L2, and then you got to go second. Quit. This one's going to be a t-test. This one's a test, not an interval. Go second, quit, and then go L1 minus L2, stored into L3. Hit enter. And once you do that, then we're going to go to t-test, choose data. Right, so I'm getting this right off the exam, 4 notes. And we know this one is not a confidence interval, right? They never asked me to form a confidence interval. It's a hypothesis test. So, so we go to that spot, go to data, t-test data, and it asks you for mu0, list. So mu0, what's mu0? Oh, I didn't even write out the hypothesis. That let's go back and add that to your exam 4 notes. I think that'll be helpful to you. So if you want to add that right here, right here. For the exam for 2 matched pairs, the HO is always mu1 minus mu2 equals 0. The difference is equal to 0. And mu1 minus mu2 is greater than, less than, or not equal to 0. That's how those will always look for dependent matched pairs. If you want to add those to your notes. All right, so let's go back then and wrap up this question. You know what? Actually, that might be confusing. I mean, that's true. What I wrote is true. But it might be more helpful to you to just write mu1 equals mu2. Because that's the same thing. And this one is, greater, less, not equal. It's really the same as the other one. All right. Either way, doesn't matter. Both are true. So, all right. So our HO is that mu1 equals mu2. What's our H1? That's a little harder to tell. Let me put this in as 0. This list is L3. Yeah, let me come on down here. So, what's our HO? Well, that's that they're equal. That's always the case. What's our H1 though? Let's write that. Yeah, notice what it's saying. It's saying test the claim, right? Remember, we always got to find the word claim and look for the words after the word claim. The claim that the diet is effective in reducing weight. The diet is effective in reducing weight. So what does that mean then? What does that mean about, remember, this is mu1, this is mu2. So if the diet's effective, mu1 is the before, mu2 is the after, and we're taking the difference, right? We're taking mu1 minus mu2 and getting some kind of answer. Do we want that answer to come out? Well, which one do we want? Yeah, forget that. Which one do we want to be bigger? If the diet's really working, you weigh more before than after, huh? We want the before to be greater. You want the before to be greater, you want the after to be less if the diet's really effective, that is. Is that making sense? What it would mean for the diet to be effective? The before is greater than the after, huh? Is that good? So just getting that out of the words of what it would mean for a diet to be effective. It would mean the before weight, the mu1, before is greater than the after weight. mu1 greater than mu2. Okay, so that means right here I choose the greater option when I'm doing the test, and I calculate. And I'm getting a p-value 0.049. So what does that mean? Did you guys get that p-value? 0.049. The significance level is 0.05. So there's the significance level, 0.05. So what does that mean? Our p-value is less than that. Just barely, but it is, huh? So the p is low. So HO must go away. So HO, bye-bye. And that was the weak evidence. I forgot to write that. Weak evidence, like always, and H1 is the strong. So we're keeping H1, which means we really believe from this data that there's strong evidence that the mu1 is greater than mu2, that the before weight is greater than the after, which means the diet's working, huh? Right? They weigh less after, and there's strong evidence supporting that. So this data they gave us is strong evidence. So we would say there is sufficient evidence to conclude the diet is not effective? No. Sufficient evidence to conclude it is effective. There we go. It's that one. So that one we had to go all the way to the final conclusion, not just stop at a p-value. Is that good? But also every now and then you can get lucky. You can have the wrong p-value, and it just all works out okay, because I never asked for the p-value. So it's a good and a bad. Anyway, questions on that one? Did you track with all that step? The main step that people have told me over the years that they get stuck on is they get confused by the diet is effective. And they don't know what that means about greater than, less than. Did everybody follow that? The diet's effective. The before is heavier than the after. The mu1 is greater than the mu2. That's what effective means, right? All right. On we go. Number 7. The data show the chest size and weight of the bears. This is the one we did, or something like it anyway. Might be the very same one. So find the equation, predict the stuff. So it's just like those other ones. Okay, so this is L1, this is L2. Regression, whenever they say regression, you know you're going to do linear regression t-test. Huh? That's all we ever do for that. So put it in L1, L2, do a linear regression t-test. So go to linear regression t-test. Yeah, so if we look on the exam 4 notes. By the way, don't bother with number, 7. Didn't I tell you to cross out number 7? Yeah, we never use number 7. It doesn't actually work on all the calculators. We're using number 9 right now. Linear regression t-test. And also you can refer to number 8. We're putting in not equals for the test, and then calculating. And then it's all about whether the p-value is less than 0.05 or greater than 0.05. I'm getting a p-value that's 0.01. Are you getting that? So that is certainly less than 0.05. That means they're linear. They have a linear connection, don't they? Remember what that means? Looking back here. If the p-value is less than 0.5, then there's strong evidence of a linear correlation. So use the equation y equals a plus bx and plug in x. So we'll do that. So use y equals a plus bx, plug in x equals, what do they want me to plug in? 45. Plug in 45. So here we go. Y equals, so what's my A value? I'm getting negative 246.44 plus B, which is 11.9799 X, and X is 45. So hit the buttons on your calculator. And I'm getting 292.6, which rounds to 293. If that p-value had come out greater than 0.05, then I would have just found the average instead. Right? We all good with following that on the exam 4 notes, number whatever it is, 9, I think? All right, on we go. Number 8, use the given data to find the equation of the regression line. Round the final value to 3 significant values. So regression line, you know what we're going to do. Linear regression t-test, huh? So this is L1, this is L2. Linear regression t-test, and away we go. This should be an easy one. And we do the linear regression t-test. We always choose the not equals. I'm going back over here showing you on the exam notes. Somewhere. Right here. So R not equal to 0. Testing for linear correlation. So hit the buttons. And I'm getting, what am I getting? I'm getting y equals a plus bx. My a is 140.4, and my b is negative 6.2. Here it is. Is that good? Be confused by the plus minus. That just means minus, doesn't it? Mm-hmm. Right? So that just means the minus. Plus and negative is just minus. All right. That was a nicer one. Number 9, Benford's Law. You know one of these will be on the exam. You saw my great excitement when we did Benford's Law, right? So it's pretty easy to read teachers. Have you gotten used to reading teachers? I'm an obvious open book, right? I like Benford's Law. It'll for sure be on there. All right, so what do you do for Benford's Law? You don't even need to read all the words if you're used to Benford's Law. It's basically just finding if a bunch of numbers fit the pattern of Benford's Law or not, huh? That's all the Benford's Law problems are. In fact, it might be helpful to go on back to your exam notes. Which one is Benford's Law? Anybody remember? Which one of our things is Benford's Law? It's goodness of fit. Go ahead and just write Benford's Law right there by goodness of fit. That's what I would do. Benford's Law is all about goodness of fit. It's saying, does a bunch of numbers fit the pattern of Benford's Law? And so you know you're getting a Benford's Law question. So have it right there. It's goodness of fit. All right, let's go back. So what are the numbers? Well, it's right there. There's the numbers. Now, the main thing is we got to keep straight the observed and the expected. And so everybody dialing in with me right here, I remember this is what has gotten people, is that they reverse these. So if you look back, let's go back again. Go back, forth, back, forth. So getting back here, notice that the what am I doing? Oh, right here. Put the observed in L1. So again, this is Benford's Law. is goodness of fit. And put the observed in L1, calculate the expected, and put those in L2. So the ones you calculate have to go in L2, and that matters. You can't just take it top to bottom. That's what gets people on this one. You have to do exactly what they're saying, meaning the observed are in L1 and the calculated, expected are L2, no matter what order they came in the problem. Does that make sense? Most other things, we just kind of take them in the order they come, huh? But it's really specific with goodness of fit. L1 is observed. Just remember, the things you're calculating, they have to go last. How about that? Whatever you're calculating for Benford's law, for goodness of fit, has to go last. So, okay, so these numbers are just handed to me. They're not calculated. So those are L1, aren't they? These are my L1 numbers. What are my L2 numbers then? They're going to come from these percentages. L2 is going to come from these percentages, like 0.301. Yeah, times the total amount. How many total numbers? Says it right there, 784 checks. So I'm going to multiply each of those by 784. And just put it in your calculator that way. Here's what I'm saying. Let me be really clear. Write down L2. So here's L1. L1 is literally 0, 12, 0, 73, 482, 186, 8230. And then L2, what's L2 going to be? 0.301 times 784. Literally type that in. Right in your L2 column. Don't figure it out on the side and then put it in L2. It won't be as accurate. You might get the wrong answer, and it's not as quick either. This is quicker and more accurate. Just put it right in L2, and then the next one, 0.176 times 784. Then the next one, 0.125 times 784. See how I'm taking each of those percentages, I'm moving the decimal over two places to make it a decimal, and I'm multiplying by 784 because it's that percentage of 784 checks. Or digits, sorry, digits. And then 0.097 times 784, and 0.079 times 784, and times 0.067 times 784, and 0.058 times 784, and 0.051 times 784, and 0.046 times 784. So that's what goes down L2. So notice the calculated ones have to go down L2. See how people naturally reverse this? Because the percentages came up top, so they tended to put them in L1. So everybody seeing that? I don't want that to get you on Wednesday or for our exam, right? You don't want to, just the percentages, the calculation has to go in L2, even though that's listed first in the problem. I write all those parentheses. You don't really have to. I probably shouldn't have done that. It's just times, huh? I hope I'm not confusing you. Just all you need is a times there. Just times. You don't need a bunch of parentheses. I probably shouldn't have done that. You don't need a bunch of parentheses. Just multiply. You don't need any parentheses on any of these numbers. Yeah, I shouldn't have done that. It's just times, right? Yeah, I'm messing up the whole thing now. It's just multiply. Just times 784, times 784, times 784, times 784. Just right on down the list. All of them in L1 and L2. Then what do? Well, it depends if you've got an 84 or an 83. Right? For the people with the TI-83, they just go program the chi GOF and hit enter. It's a little quicker. For the people with the 84, stat test, chi-squared goodness of fit test, and you got to know the degrees of freedom, which is number of categories minus 1. So if you're an 84, the degrees of freedom, number of categories minus 1. So it's going to be 9 minus 1, because there's numbers 1 through 9, right? So 9 categories, 9 minus 1, 8 degrees of freedom. Your TI-83, you don't need any of that. And then calculate. I'm getting a p-value that's 0. You getting a p-value that's 0?
Yeah.
Comes out 0. Now what? I didn't write down the HO H1, did I? It'll say it here for us though. HO observed and expected fit. H1 they do not fit. Notice it's right on our sheet there for us. HO they fit. H1 they don't. So HO they fit. H1 they do not fit. And you know how the evidence goes. Weak evidence, strong evidence. So our P is super low, right? 0. So the P is low. HO must go away. Bye-bye HO. Keep H1. There's strong evidence that they do not fit. There's strong evidence that the pattern of digits does not fit. So what does that mean? So there is sufficient evidence. Yeah, it's going to be one of these sufficient evidence. Therefore, we conclude that the checks are not the result of fraud or definitely the result of fraud. Which one is it? Yeah, definitely the result of fraud, right? Because they don't fit the normal pattern. Remember, the Benford's law is the normal way that leading digits go unless they've been monkeyed with, huh? It's interesting. It's that predictable. We as human beings are that predictable in how we write leading digits. And so if it doesn't match, you know something funny's going on. Strong evidence, something funny's going on. Fraud in the checks. Is that good? We're getting close, but we're running. Let's see. In studying the responses to a multiple choice test question, the following sample data were obtained. At the 0.0 significance level, test the claim that the responses occur with the same frequency. Find the p-value. So what's that going to be? Test the claim. That's always the most important word, huh? Test the claim that the responses occur with the same frequency. Same frequency. What does that mean, same frequency? Look back to our exam 4 notes. We're still doing goodness of fit. See the phrase right there under goodness of fit? Equal frequency. Same frequency. There it is. So how do you do it in that case? Total number of values divided by number of categories. Total number of values divided by number of categories. Let me go back and, so that's the help, but let's make sense of this. What are they really saying? Let's try to be real here. They're saying people are answering a test, multiple choice, right? 12 times they answered A. 15 times they selected B. 16 times they selected C, etc. And they're asking us the question, test the claim that they answered everything with the same frequency. In other words, they did the same number of A answers as B answers, as C, as D, as F, or E. A, B, C, D, and E. Same Well, if they did same, what would that be? How many would that be? Like, how many answers? If they really made the same, we're looking at the data. They didn't answer them all the same. But let's figure out what that would be. If they really were answering them all the same, how many A answers would there have been? We have to add them all up and divide by 5, huh? Because there's 5 different options. So if you add them all up, 80? So, 80? Okay. 80. And then so each should be 80 divided by 5, which is 16. So each one should be 16. So 16, 16, 16, 16, 16. So if they were all the same, so this is like a bunch of people all took a multiple choice test. And the teacher afterwards wondering, did they all just totally guess and they have no idea? And so his or her thought is, well, I'll test and see if they all just answered about the same number of A's, B's, C's, D's, and E's. I mean, it didn't come out exactly the same, but it's close. Is that evidence that they were basically just guessing the same number of A's, B's, C's, D's, and E's? So let's try to calculate it. So it's a goodness of fit. This, remember, L1 is what's observed. L2 is what we calculated. We just calculated those 16s, didn't we? So that's got to be L2. So put the numbers in L1 and L2, and then do a goodness of fit test. Goodness of fit. So put them in L1, L2, and then go do the goodness of fit test. What's the degrees of freedom for the TI-84 people who need to do degrees of freedom? Number of categories minus 1. How many categories? 5. 5 categories, so the degrees of freedom is 4, huh? A, B, C, D, E are the categories. So I'm getting a p-value that is 0.7587, which is, none of these. It's about time for another E. Were you just feeling it? I was feeling it. All right, so that makes sense that that's goodness of fit. So let me go back real quick to the goodness of fit thing. See how on the goodness of fit chart, exam 4, number 10, here, exam 4 notes, I'm saying you have to calculate the expected values and put them in L2, and there's 2 ways. If it says equal frequency, you do what we just did, total number divided by categories. If there's categories percentages listed, it's each category percentage multiplied by the total values. The 2 different ways we figure that out, huh? We just had those 2 examples on that. Does that make sense? You ready for both those goodness of fit type questions? Questions on that one? You good there? Are we good? So let's move on to number 11. Table below shows the age and favorite type of music of 668 randomly selected people. Use a 0.05 level of significance to test the claim that age and preferred music type are independent. Nobody believes that, do they? Age and music type are independent. So age and music type, are they independent? So guess what this one is? Test for independence, right? It says it right in the words. What could be easier? Well, probably a lot of things, but yeah, that's what we want to do. So going back to the exam 4 notes on that. So number 11, test for independence. So HO is that the row and column variables are independent. H1 is they're dependent. And you got to put the thing in a matrix in your calculator. So we'll do that. So we got to go second matrix And when you do, you got to go over to a couple times to edit and hit enter. And then you got to do the size. What's the size of this one? 3 by 3, right? And for the size, 3 by 3. And then put in the data. Put those numbers in there. And then after you do, then you go to Stat. Go over to Tests. And you're going to choose just the general chi-square test. Not the goodness of fit. Just the chi-square test. And just hit a bunch of enters on that one. So there's the p-value I get. 0.115. You guys able to get that? You guys probably already finished ahead of me. All right. So I'll move on. You're all good there. Number 12. 160 students who were majoring in either math or English were asked a test question, and the researcher recorded whether they answered the question correctly. The sample results are given below. At the 0.05 significance level, test the claim that getting the question correct, incorrect, and major are independent. So that's another test for independence, isn't it? They even says the word independent right there. So same kind of thing. Got to go second matrix. And go over to edit. And hit enter. And the size of this one's going to be 2 by 2. And then put in the 4 numbers. And then do the chi-square test. And get a p-value. I'm getting a p-value 0.01077. And you guys getting that okay? All right, good. And now we want to compare that to the significance level. So the significance level is 0.05. So how does that compare to the significance level? It's less, huh? The P is low. The HO must go away. So I never even wrote the HO. The HO, let me write it somewhere. The HO was that they were independent. And the H1 is the opposite of that. And that would be that they're dependent. And the HO, there was weak evidence for it, like always. H1 strong. So the HO must go away. So cancel out the HO. Keep the H1. There's strong evidence that they're dependent. That, in other words, what you get on the questions, how many you get correct on the test, has something to do with your major being in math or English. Maybe it's a big grammar test and the math people are failing out. So whatever the test is, it's affected by whether they're a math major or an English major. They're dependent. You might want to write that in if that's helpful to you. I'll go back and write that in over here. For the test for independence, HO, independent means do not affect each other. Whatever the variables are, they don't affect each other. And dependent means they do affect each other. That's what independent things mean. Now, if things are independent, they're separate. They're not affecting each other. But if two things are dependent, then they depend on one another. They affect each other. That's what it always means when you conclude independence or dependence. on that. So you might want to add that to your exam 4 notes if it's helpful. So then, going back to the question, what was our conclusion? Dependent, which means they do affect each other, don't they? What does? Your major, math or English, and how many questions you got right on the test. Those variables, your major and your score on the test, affect each other. So which one is our conclusion? Sufficient evidence. See this one right? Sufficient evidence. We conclude the major is not related? No, that's not right. Oh, is it the next one off the screen? Okay. Oh, it's up here. Sufficient evidence. Therefore, we conclude that the major is definitely related to getting questions graded. Yeah. There we go. That's the answer. Is that good? 2 more to go. Number 13. Which one of those scatter plots goes with negative 0.996? Can you tell which one of those it is? Yeah, it's the one negative, so it's going down, right? So it's not 1 or 2, they're going up. And it's not down perfect. You know, this one would be negative 1.0. This is ours, right here, number 4, huh? Because it's negative, it's down, and it's not quite perfect, but it's almost perfect. Remember, when R is 1.0 or negative 1, it's a perfect line going up or down. And when it's close to 1 or negative 1, it's almost a perfect bunch of dots going up or down. So there it is. That'll be your favorite question on the test, right? Nice, easy one. Nice and quick, nothing to do in the calculator. On we go at number 14. There's only 14 questions, which is good and bad, isn't it? So the paired data below consist of the cost of advertising in thousands of dollars and the number of products sold in thousands. Find the value of the linear correlation coefficient. I thought we did that once already. Huh. Something else, I guess. So yeah, so just put them in L1 and L2 and do linear regression T test. Regression T test. And you always choose the not equals. And we come on down, calculate, and I'm getting, if you go down to the bottom of the screen, there's R squared and then there's R. R is 0.7077, so 708. There it is.